That's what I said.
Yes. All right, let me get out of your way. All right, so.
Okay, all right, ready.
Okay, so our group did these little. What?
Not yet.
Not yet. I'm sorry. What? Okay,
No,
our
you
group
go.
did these little like Kool-Aid things. They're called Zip Fizz. You can get them at Costco. I'm marketing for them. There's also like some protein thrown in there. We tried pen ink originally, but we threw it in water and it did not mix. We should have thrown in alcohol. We didn't know that. So we tried this instead. And then these are our graphs. Do you want to show the graphs?
Yeah. So this is the wavelengths that we found that they would absorb well. This one absorbs most right around 400 nanometers, which was
What color is that?
grapefruit. That's the grapefruit, which would be
What color is
pink.
400 nanometers?
Well, that's right around purple, which we're not
just keep going.
entirely sure why that is. And I think all of them peak right around 400, but that kind of makes more sense for these. This was the Pina Colada, and as you can see, it has a pretty similar curve.
Can you put the other one back up? Because I think the other one had two little peaks.
Yeah,
So this one has a peak at 400 and another one where,
it's right around. It's right around 550.
okay. So I know you say similar, but you are looking for something different.
Well, yeah. This one doesn't have quite the same peak,
Okay.
but as you can see, there is a slight
Yeah.
flattening around
Yeah.
550, and it absorbs least when you get over to red at 900 nanometers. Or I guess that's not red. That's around
700 red.
okay.
You know, 6.
In
57.
infrared and red over there, it absorbs the least. And then for the black cherry fizz, it's a much smoother curve than the others, which we found really interesting.
You all do it on the same day?
Yeah,
And one of them just came out smoother?
yeah, it was kind of odd, but it also kind of has a somewhat similar shape. Peaks right around ultra or violet and ultraviolet, right around 400, and then it has a slight flattening or
Yeah.
kind of slight hump at 550, and tapers down at around red and infrared.
Do you want to talk about the
So it's kind of weird for all of these to have a peak around purple because the black cherry was more of a brown color, the pina colada was more of a pink, and this one was just clear or yellow in general. So what we decided to do was shine UV light at the Zip Fizz, and it turned out, with the black cherry at least, that it came out like a glowing green, and we didn't know why. So EJ did some research and he couldn't find anything. But we were leaning to the conclusion that it could be the vitamin B12 that's in it, or the sodium, because they glow green under UV light.
So you did a little research looking to see maybe why it fluoresces?
Well, I can show. There's a ton of different like vitamins and proteins and stuff in it. But so I kept looking up. I literally just looked up. Does this element glow in a certain color? Does it glow in this color? And I couldn't really find anything, especially because they were all kind of mixed into it. So there probably wasn't like just pure sodium or pure manganese or whatever was in there. So I wasn't able to find any conclusive data, and there's not a lot of people that are shining black lights at their drinks. So there wasn't a lot of evidence to show what it was in it.
What they did was, some of you did leaf extracts. Raise your hand if you did some kind of leaf extract. Just one group? Okay. Chlorophyll is famous for being fluorescent, meaning if you shine a bright light on it, even though it looks green, if you shine a bright light on it, it will fluoresce red. it'll absorb all the wavelengths, but it'll actually give off a red wavelength. So if I don't use a bright light, it just looks green. If I use a bright light, it'll actually fluoresce red. And yours, how many of these fluoresced with UV?
Mostly all of them. Like the grapefruit shined a little less, but you could still see it.
But it didn't fluoresce. Same, did it fluoresce the same color?
The
Yeah,
same hue of green, yes, but some were more faint than others.
Different
Like,
Kind of a greenish, right?
Yeah.
That's interesting.
this one we could see it the most. I showed you the other day how green it turned out. The solution we made got thrown out. But
You don't have to, but just for interest, if somebody were to email the company and say, we're doing some experiments with a spectrophotometer, we noticed that, with the UV light, yours fluoresced green. Can you tell us, what is there? And they have chemists that work for them. They'd be able to tell you. I don't know. So if anybody if you want to do that for extra credit.
I got curious with I think Caleb's group, or Kyle's group, I don't remember, with their drink with vitamin water, because with the orange one, it also did the same thing as it did with our graphs.
Which one? Vitamin water?
The orange one,
Huh. But
it
not
did the
the
same
red.
thing with our graphs, but it didn't glow green. So
Okay,
I don't know.
That's why I like, this is real science, what you're doing in here. I don't know the answer to this, but, it'd be interesting to find out.
I'll shoot him an email.
And especially, with the use of the vitamin water does also. I've heard, tonic water, you know, tonic,
It glows.
I've heard tonic water will do that also. So, all right, what do you think? Any questions for this group?
Can we see the thing, the light?
You wanna show them? Can you show them?
We tried it just a few minutes ago, but the concentration we had wasn't strong enough for us to give.
It's possible that, the chemical degraded over time, it's possible. That sitting here for like last 4 days, it's possible that that's.
We
what happened.
Well, no, we did like an
we made a
index.
fresh one, but the concentration was different, so it didn't work.
Oh, it worked, but it wasn't as strong as
Yeah.
it was when we first did it.
Okay, I don't know what that means, that's interesting too. Okay. All right, anybody have questions? All right, very good. All right, thank you. Okay.
Whoops. Hello. Tell you what I'm gonna do. I'm gonna save a little bit of time. I'm gonna just give you back your spectrophotometer quizzes, and what I'd like you to do is, if you'll take them home and look at them, and then tomorrow, the first thing tomorrow, you can say, hey, I was looking at this, and I noticed you marked this wrong, and we can go over the answers there. But I'm gonna save just a little bit of time, and so if you'll just take them and take them home with you, see if you can figure out what it was on your own. And then I will definitely wait, if you'll wait till tomorrow, I can, first thing tomorrow, I can show you the answers and that kind of thing. But I think right now I'd like to get going on this, so. I decided to make it worth really 65 originally, and let's make it 70. And it's almost like you got 5 out of 5, questions right. But so if you saw a little scratching out here, that was out of 65, so I made it out of 70. It actually helps you a tiny bit, So anyway, there's yours. And again, take it home and come up with if you have a good argument or something on you, or something about some points, you have a good argument for me, I'll listen to that.
This is the rest of our experiment, by the way. Or like all of our, this is like all of our data and stuff.
I need, that's it?
Yeah, that's it.
I need that. You start doing that. All right, so again, I don't mind if you look at it right now, you can, but say, I'm going to take it home, I'm going to look at it a little bit more detail. And, and then tomorrow, since we spent so much time building the models and the presentation, I want to kind of get off to a good start today. All right, don't forget, you're reading a packet at home, and I got that from a book. I thought it was a very interesting book. It's called Conceptual Chemistry. And it's kind of like in this flavor of conceptual physics. And I really like the book, but the book that we have for our class is very, very much like you would see probably in most of your bigger universities. It's used for AP, we use for college, so I decided not to go with that book many years ago. And so what we'll do here is I'll spend a little bit of time with that packet and model building, and then what we'll do is we'll switch back to your book, and we'll get into your book and how they do organic chemistry in your book, and that'll be what they might have done at that level, like maybe first year chemistry level, something like that. Okay, is everybody ready? Everybody right? And again, just as far as the quiz, just take it home and say, I'm gonna look at that. I'm gonna look a little carefully at that, see what I wrote down here, that kind of thing. All right, well, first of all, I'd like to know, I hope you are a little excited about this. I like the whole idea of getting something brand new for you. I will tell you that if you go to college and you are a science major, they will make you take a minimum of 1 year of what they call inorganic chemistry. Got that? So that's kind of the stuff you already kind of had. And they're going to throw some other things at you. They might throw thermodynamics. It depends on where you go. Some people don't like to do that in the first semester. Some colleges say, yep, I'm doing it. And I can't predict that. Does your professor at that university say, oh, I know you're all smart, so I'll start with thermodynamics. I'll show you. I've seen that. I don't think it's a good thing for people to do. I've seen, I just got a letter from Adam McIntosh. He was at NC State, and there were 500, and did I tell you this story? There were 535 people in his class, and he finished his first semester at number 5. He had 102 average. Now, of course, he's smart, but you are too. You are too. But he didn't mention anything that really thought it was like over the top, and that was at NC State. He didn't mention, hey, they spent a whole month on something else like that. And then also they'll make you take a minimum of 1 year organic. If you're doing anything in the medical field or anything like that, even though you're not going to be an organic chemist, they want you to know, hey, you at least heard of that word, haven't you? Ketones and aldehydes. You've at least heard that stuff, haven't you? So they're going to make you do that. I'm not here to teach a whole year of organic chemistry, just enough to say I can get a good start. I also noticed that when I teach this, people that take biology, they have a lot of organic chemistry in biology, and it actually makes more sense to them when they take their college biology class too. So I'm hoping it's going to help you. I'm not a substitute for a whole year of organic chemistry. I'll tell you that right now. All right. Well, first of all, what's interesting about organic chemistry is if you take a look at number 1, carbon itself is not that reactive. If you laid a bunch of soot on the table and waited a long, long time, probably not much would happen at all. Maybe if I could heat it really hot, it might join with oxygen in the air, make carbon dioxide. It could do that. Could even make carbon monoxide if I don't give it quite enough oxygen. It's not really that reactive, though. And yet, over 99%, 99.5, 99.8, of all the compounds humans have ever discovered, the number just keeps getting bigger and bigger and bigger. So that number, I used to have 96, 90. It's after 99 now. Most of the compounds on the planet are organic. They're carbon compounds. So what's interesting is most high schools, they don't have time to do organic in first year, even in honors. And if you don't take a second year or AP, oh, by the way, I forgot to tell you that, until about 7 years ago, that was in AP chemistry. And I hate to tell you this about games that people play, but the people who make these tests, they don't like it when lots of people start scoring higher and higher and higher, when teachers figure out, I can teach to that test. And so they knew that there was so much stuff in AP chemistry that how deep could you actually go in organic? and they were figuring out you could, in a class, you could teach people the basics of organic, and they're going to score very high on that section. They did the same thing with nuclear, and nuclear used to be part of it. I'm going to teach nuclear, but the both of those are not on the AP test anymore. So they didn't like, I'm putting this in my own words, they didn't like it that people were getting higher and higher scores. They knew if they only covered a certain amount of nuclear, how deep could they go, and people are getting a lot of those questions right. So, but anyway, long story short, if over 99% of the compounds ever created or discovered are organic, they're not even being taught in AP now. They're not taught in first year. They're not taught in second year. When are you supposed to get it? College. Okay. Now, let's go to the next one. We're talking about carbon. It's a star. Carbon is a star for sure. And we know up here, if you look at the periodic table, how many total electrons are in every carbon atom? So how many total electrons in every carbon atom in the universe? Well, as long as it's neutral atoms. How many? Everybody knows. Everybody. 6. Okay. So every carbon atom has 6 electrons. Is that right? Yes. Now, we're going to, at the end of the year, we'll do quantum mechanics. We'll get back to electron configuration. But where are those 6 located? Well, I happen to know that carbon is in the second period. So it has not one energy level, but it has 2 energy levels that has at least some electrons in it. And the first energy level only needs 2 electrons to fill it. So that must be 1, 2, 3, 4, 5, 6. Okay, that's 6 electrons right there. If 2 are in the first energy level, then how many are in the valence electron? How many valence electrons does it have? 4. And of course, there's a Roman numeral right there. 4. Okay, so that reminds you that carbon has 4 valence electrons, except for the first energy level. Level 3, 2, 3, 4, 5, 6. All of these have something in common, except for helium. They all have 8 electrons in their valence energy level. 8 seems to be the magic number, the stable number. If you put 8 in my outermost energy level, I won't react anymore. And that's where the most non-reactive elements are found. So oxygen has 6. Carbon has 6. And so it would tend to do, if I could gain 4, I could do that. Gain 4 electrons. I could possibly do that. I could also lose 4 electrons. Losing 4 electrons is not the easiest thing in the world. And how do you gain 4? Are you going to steal 4 from somebody else? And what I find that carbon's like right in between that number 8, right? So the best way to do it would be to share or cooperate, right? And so that's why it forms a lot of covalent compounds. So one of your electrons and one of mine, that's a pair we can share. Hey, one of yours, one of mine, that's another pair. So carbon would like to form 4 covalent bonds. So if we were to write this down, carbon is going to have, in your model building kit, you're going to have these 4 holes in it, and you're going to put 4 sticks in them. So carbon is always going to have 4 covalent bonds in it, unless there's something weird about it, okay? Another character that's going to come into play is hydrogen, and hydrogen is unusual, only has 1 electron, but how many would it like to have to fill the first energy level? 2. So 2 is a magic number for that energy level. And so how many holes would you think the hydrogen would have in it? And how many sticks should come out of every hydrogen? 1. Okay, so when you build your models, you'll notice there'll be 4 sticks here, there'll be 1 here. What about oxygen? See if you can figure that out before I tell you. Oh, very fast. 2. There should be 2 holes in there. And what about nitrogen? And nitrogen, even though the model kit you have has 5 holes in there because nitrogen can do some weird things. But most of the time, nitrogen is going to try to form 3 bonds. Has everybody got that? All right. Now let's go back. And carbon has 4 valence electrons and mostly forms covalent bonds, and it can bond with 4 other elements. That's kind of unusual. I'm going to try to tell you why are there so many carbon compounds. Number 1, by having 4 valence electrons, I could form a bond with 4 different atoms, couldn't I? That's pretty high in the chemistry world to form bonds with 4 other things. Number 2, carbon can form long, short, straight, branched chains. It can make chains. It can bond with itself. It can bond with itself. For example, I could have something that had a string of 10,000, 50,000 carbons. You can have 50,000 carbons in one molecule. Carbon, 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 carbon. So carbon forms bonds with itself, and it also can form what they call chains. Now, the chains can be straight, and we're going to be making some of these, or the chains can be branched. Here's a branch. See, there's my straight chain, and here's a little branch, you see? That's called a branching carbon, organic compound. All right. It can also form ring structures, and you'll find that out. You're going to make, here's one. We can make a ring like this. We can make a ring with 6 carbons, 8 carbons, 6 very common, 3 carbons, something like that. So it can make a ring structure like that. They also, here's some other reasons why. Carbon can form single bonds. See the 4? It can form 4 single bonds. But what else could it make? This guy has 1, 2, 3, 4. It can also make double bonds with itself. Carbon, carbon, carbon single bonds, carbon, carbon double bonds, and carbon, carbon triple bonds. Now that's upping the variety. You can see what's going on here. The variety of carbon compounds is huge. It's going to be huge. When carbon forms 4 covalent bonds with 4 different atoms, a tetrahedron shape is going to happen, and I'm going to show you that in a minute here. I want to mention something that I don't know how much you remember here, but do you remember the electron configuration for carbon? Remember the 1s2, 2s? What do you think? What's carbon? What's going to be right here? 2, 2p, 2. Do you remember that? We'll do that again. We'll do that again. Anyway, so what happens is the first 2 electrons are in the first energy level, and they're in a thing called an s orbital. And the next 2 are in the second energy level in an s orbital. It looks kind of like a ball. And then there are 2 in these little dumbbell-shaped things that are called p orbitals. Now, what's interesting is, do you remember any of this? Do you remember any of the electron configuration? Okay, so what would happen is you would have an electron here, and it would be going clockwise, counterclockwise. And then that's 1s, and then the 2s you go whoop down there, and then you have the p orbitals. And there are 3 of those, and you go whoop there. All right, now I'm not spending a lot of time on that. We will have that at the end of the year, but here are my 6 electrons. See that? Now, if you looked at it, you'd say, well, there's already 2 in that orbital. They don't look like they're going to want to react, but it looks like carbon would like to pick up 1 more, 2 more, 3 more, 4 more. How is it going to do this? How's it going to do this? It looks like it only has 2 that it's available for sharing. Yet carbon wants to form 4 bonds. So it looks like it only wants to form, I don't know, I only have 2 more that I can share. And something really weird happens, okay? Well, it's not weird, it's God. But God, here we have the s orbitals and the p orbitals. Okay, s orbitals, this much energy. P orbitals, this much energy. So what carbon does, it rearranges these 4 electrons into a hybrid. Everybody know what a hybrid is? Like a hybrid car is part gasoline, part electric, right? A hybrid. A little bit of this and that. In biology, 9th grade, big T, little t, that was a hybrid. Well, anyway, so what happens is these 4 electrons are not going to be in the s orbital anymore. They're not going to be in the 2s. They're not going to be in the 2p orbital. They're going to be about here. And all of them are going to be in what they call an sp hybrid. Wow, now that's pretty amazing. In this case, all of these electrons are now going to be equal. They all are going to want to form bonds, and they're going to want to form 4 covalent bonds. Now, I won't get too technical. I want to get into model building as soon as we can, but are you okay with that just temporarily? It's a weird thing. It's not an s orbital. It's not a p. It's an sp hybrid. It's kind of in between. All right. So anyway, let's talk about this right here. Unfortunately, when you look at books, I'm going to write this compound right here. Let me go ahead and I'll draw the structure, and then I'll write the way the book has, okay? Now here's the way you might see this thing in a book. This is called methane, and we'll talk about how to name compounds very soon, but methane is CH4. So the compound is CH4, and this is one way to draw it. Now, there's nothing wrong with that because paper is two-dimensional. So if I have to try to represent this, it's actually very difficult to draw this on paper. You see that? It's not that easy to draw that, a three-dimensional thing on paper. So a lot of times they just draw it like this. And as far as I knew, for a long, long time, that's what methane was. It was flat, and there was carbon in this height. But really, what's really happening here is there's a carbon inside here. And here's a hydrogen, a hydrogen, a hydrogen, a hydrogen. So the carbon's inside there. And that's what it looks like. And so I went ahead and made one. And that's why I think model building helps a great deal, because this is what you think methane is, but this is actually a little closer to what it looks like. And so here's a carbon atom, and it has 4 bonds. Each hydrogen atom has 1. And they actually try to get as far away from each other as they can, and they did. And it's about a 109-degree angle. And this structure, believe it or not, this tetrahedron structure, is seen all over the planet in organic chemistry. So you're going to see one tetrahedron together, maybe 2 tetrahedrons together. See that? Now, what's the difference between a tetrahedron and a pyramid? Pyramid does have 4 sides, and what's the base? It's a square, isn't it? A pyramid has a square base, and therefore it has 4 triangles that come out, doesn't it? But this is a tetrahedron. What's the base look like on a tetrahedron? It's a triangle, and it has 3 sides like that. So again, there is a difference between a tetrahedron and a pyramid. Okay, so this is kind of an interesting shape. And when you start building your models, look for this shape here. Another thing I want to talk about is the book may represent methane this way. You may set something like that on your handout sheet, okay? And if you're lucky, somebody took the time to try to draw a 3-dimensional structure. That's hard. But I want to show you another thing they have. This right here is called a ball and stick model. A ball and stick model is made so you can see every atom and see every bond. Ball, stick. The sticks are covalent bonds. See? 1, 2, 3. They're covalent bonds. The balls are atoms. There you go. But a lot of your modern books have gotten to the point where they have graphic artists. And this is methane also. Can you see that one? Now, this is called a space filling model. A space filling model says, hey, if you're smart enough to know how many bonds methane has, well, we don't need to show them. If you know it's if you know it's 4 single bonds, why don't we make it a little bit more like the real shape? Let's make it look a little bit more like the real shape of methane. Does everybody see that? So when you go to college and some of your textbooks, whether it's biology or chemistry, biology for sure, they're going to use drawings. And I wish somebody would have told me how important it was to understand those drawings. Okay? So anyway, they sometimes use the ball and stick model, and sometimes they just use the paper drawn model, right? And then they do this thing with the space filling model, and that's what a lot of your books are doing now. And okay, yeah, Tim.
So, doesn't the space build model, like the atoms aren't that close together?
Well, that's a good question. Every model has limits, like how close can the hydrogen? I think you can actually look these up. If you said carbon-hydrogen single bonds, what is the bond length? You can actually look that up. And you have carbon-carbon bonds, bond length. You could look that up too. If you want to look that up, I'll give you some credit for that. Look for any kind of carbon-hydrogen, carbon-nitrogen, carbon-carbon bond, triple bonds. see if you can find a distance, and that's the distance between the center of both atoms. Okay, all right. Hey, give me about, 30 more seconds. Hang on. So, I want to show you something here. Let's go right here. In some cases, this is what you're used to in what they call first year chemistry, okay? You're used to, and by the way, in organic chemistry, the order is Chan. I'm the most important. You're mostly next important, next Chan. Everybody got that? So if you want to know what order, it's usually that order. And so look at this molecular formula, C2H6O. But what I like is organic chemists like to do this, a structural formula. Do you have any idea how that's put together? No. And so they have their own way of talking about a formula. Look at this right here. See that guy here? Ah, watch. CH3O, CH3. And that's the way they would write the compound. Because this doesn't tell you how it's put together, and this does. And look over here. See this guy? C3H7Cl. Ooh, what's that look like? You don't know. Okay, so I'm going to write this way. CH3, CH2, CH2, whoops, CH2, Cl. Now do you know what it looks like? Okay, thank you very much. And tomorrow, I want you to either have one partner, or I don't know if I have enough kids to everybody do by. I know everybody can't do it by themselves, but I had to have a lot of groups of 2. But if I had to have a group of 1, I could do it.
Thank you, Mr. Green.
All right. Bye.